A very warm welcome and greetings of the day to everyone. My name is Neda Yunis, Dean at DBS Language School, and I'm joining you from Canada. I'll be hosting today's session where we'll explore some exciting insights in structural engineering. We are very pleased to be joined by Dr. Simon Bechara, a civil and structural engineer with over 30 years of experience in steel structures, pre-designed buildings, and reinforced concrete designs across the Middle East, Africa, and Asia. He is recognized for pioneering engineering software for steel system and has held leadership roles with Kirby Building Systems, Zamil Steel, and now as the founder of Matrix.faq Engineering Consultancy. His expertise spans structural design, seismic analysis, and large-scale project leadership. Welcome, Dr. Simon.
Thank you very much, Mrs. Nada. I'm very pleased to welcome me in this excellent meeting, and I'm very pleased to be with you today. Thank you very much.
And today's discussion would focus on the topic modified equation of Vlassov transitional behavior of thin-walled members. This topic deals with how slender structural elements like steel beams and thin-walled members twist and deform under loads. It also looks at how mathematical models like the Vlassov Theory are modified to be better in order to predict the real-world behavior and improve engineering designs. To start, Mr. Simon,
Yes.
Dr. Simon, could you please introduce yourself and tell us a bit about your background and what inspired you to work in this area of structural engineering?
Perfect. I'm a structural engineer since 1991, and I started my life with research during the master's days in finite element and structural analysis, and I had the chance to make the theory into real ground by starting programming structural analysis in 3D environment and design. And this is where in steel structure I faced the first reality that most of the FEM applications does not really focus on the warping and the steel design in a proper manner. In particular, in steel buildings, industrial buildings, we have the crane behavior, the crane beam behavior, where it is subject to warping. And this is clearly highlighted by the codes, by the Americans and the European codes, where always we have to take the crane beam aside, make a separate calculation, and then take it back into our design to present it to the client in a safe manner. On the other hand, this information might not really be known to most of the engineers in the market unless they are really supervised by senior engineers. So because I was writing that software for the company, and then I said to myself that I have to fix this problem in a way or another. So Vlassov equation, it was not really practical at that time to be embedded into FEM applications due to some accuracy or due to some in some positions that equations is not really solved.
So there were a lot of challenges.
Exactly. So I started my own proper calculations myself, and then I ended up to another form of. I found out that the shear forces. I'm sure that the structural engineers might really understand what I'm talking about. That it is in the form that the shear slide plus the warping force that is applied on that element, but also there's another shear slide that is applied on the flanges of the I-beam, for example. and that shear stresses or forces are not really the movement of that shear slide is not really represented in that equation. And then I said to myself, then this shear slide should be represented in a way or another because it's going to add another rotation and another displacement to that member. Then I made an additional work to myself personally, and it was this research is done 100% by myself. And then I ended up to the result that yes, an additional movement will be there, and additional rotation shall be added to the equation of Vlassov. And then finally, I resulted, the conclusion was that an additional rotation will be added to the final result coming from the equation of Vlassov. And then the Vlassov equation is not really the final result of the torsion and the effect. Then coming back to the question, what will be the effect of this? Then the effect of that will be more significant on thinner wall members, elements such as cold formed, such as built-up sections, thinner built-up sections, open circular form, because we used to study that open circular form, we have to apply Saint-Venant, but I think that in that case we have to apply the shear slide in a different way, adding the warping to that circular open wall, which is also is going to give us quite different results, and hitting the problem also further and further. Then why this equation cannot be applied on the finite element applications worldwide is that working further on that, because the number of equations is not really enough to solve all the number of unknowns for that problem. So what could be the solution for that? Also, I made a further work on that.
Can I
and
ask you something? So there
Yes,
is
please.
not one solution for these problems. So every problem has to have its own specific solution, I believe.
I think we need to think out of the box. And a beam element, instead of representing it by a finite element, some people think like that, or actually we are thinking like that. So a beam element, instead of being represented by 6 by 6 degrees of freedom, which is 12, then instead of going by a finite element, it's going to take like thousands of hundreds of number of degrees of freedom, which is going to make the problem much more complex if I have a high-rise building, or if the number of elements is going to be larger. So finally, our machine or our computer has a limitation. So why not thinking out of the box and creating another stiffness matrix for that beam element, which is going to be 18 by 18 or 24 by 24, which is going to create a larger stiffness matrix, but still much lower than the finite element solution that is existing now and still limited to solve a large structure element. And why not obtaining a much more accurate result for C structure, in particular built-up members and cold form elements? Because these stresses are still hidden in our analysis, and they are not really visible. In particular, cranes, which we cannot really ignore it, severely torque elements under torsion, severe torsion, which also we cannot ignore, bridges, warped elements. Always we have to take them aside, make the calculation, and then come back again to our structures. This is not really practical in
It's pretty much the heart of building
exactly
big stuff out there.
Exactly.
Amazing. So what kind of drew you to studying this field? I guess it's a very niche field, right? And also, if you can, in one sentence, if you have to explain this concept to a layman, how would you explain that?
If I want to explain it to, pardon me?
If you want to explain this concept to a person who's not familiar in this field or to this field in one sentence, like in the most basic way, if you have to explain this concept to a
Okay,
person,
thank you
how
for the question. The beam element that we are using today is not really sufficient to represent steel beam element in all its behaviors. And I think uh, let's not really go to the numerical analysis all the time because we don't want to think. And always we are always counting on those, let me say, really genius people who passed through our history, like Timoshenko, like Saint-Venant, like Einstein, like the people who to make the foundations of the elastic theory. I'm talking about engineering. And why not really try ourselves to dive into the theory again
Mhm.
and not always counting on the machine because the theory will make is going to be combined with the machine to give us a much better results.
Of course, of course. And
That's
yeah, like, so
that's the
going
idea
back to the
behind.
question, so what drew you to studying this field? Were you
Um,
always like a very excited kid to do something that has, like, in the field of engineering?
I am, yeah. I'm always like that. I'm always like that, and I think that finally we as human we have to always work for to build a better world,
Yes, yes,
to keep developing for the future, to enhance. If not for my days, why not really sharing this information for the next generation?
generation. Yeah,
Why not be sometimes we're in somehow in some corner be the good example somewhere in a small part in our life to the
true.
other generation
That's what makes it
and
worthwhile.
and give them the excitement and the boost that yes we can work again and it's not really always uh, to be on the surface, so let's really be more human in our values and in our thinking,
Yes,
and because really God gave us this word to observe and put the problem in front of us and give us the capacity to a certain level to solve it.
and with your research, I'm sure it's like a great way of giving back, right? Because you wanted to always do something for the world and you wanted to be kind and stuff. And with this
Hopefully,
research, hopefully, yes, with this research, you're going to make sure that, yes, you are going to be leaving a gift for the generations to come.
hopefully again.
Okay, yes, fingers
Finally,
crossed.
finally,
All the
yeah,
best.
hopefully again, finally, other people, other old generation shared that information with me, and then hopefully I could took advantage of it, and I put some small stone, and then this small stone I have to give it to the future generations, and this is where how life continues.
Yes. Okay, going with the next question. So,
Yes, please.
what limitations in the original Vlassov theory led to the development of modified equation?
Um, the missing additional rotation and movement that the stress is there, but the movement of that stress was not really considered.
Mhm.
Uh, Also, another point, which is now you reminded me by your question, you reminded me of that term that I have introduced that I call the bi-shear.
Mhm.
Uh, the term by moment existed, but the derive of the by moment led me to the bi-shear. And that bi-shear has a movement, has an additional rotation, which was not considered in Vlasov. So, and since we were talking last time about the AI, I
Mhm.
was really surprised that on one of the sites, the AI has looked into my research. And, and the AI by itself told me that a new term Bi-Shear has been introduced, and this will do the 1, 2, 3, 4, 1, 2, 3. You see, the AI has given attention to my research where humans did not. It was really
So it's a good collaboration.
that as is the AI start paying attention to us where we are not.
Even though we don't want the attention, it's like, let me give you more attention.
Yes, this was really surprising for me. And the most surprising and more surprising is that when I told my colleagues that, gentlemen, the AI has given attention to what I have said, they were more serious in my work, more than telling them that, gentlemen, I have done this myself. No, they are not interested. But if the AI said it, they took it more seriously.
They took it
If
more
the
seriously,
AI,
like, wow, this is a serious thing, right?
if the AI said it, then it's serious.
Wow, I love it. Okay, thank you so much.
Thank you.
So, how does this research impact real engineering structures like
More
buildings and
accuracy,
bridges?
more accuracy, more
More
accuracy,
accuracy, perfect.
more safety,
Mm-hmm, mm-hmm.
more
And
safety. And this will have a direct impact on the codes, on the design codes.
mm-hmm,
Let me say, in the part where the lateral torsional stability is
mm-hmm,
always there in all the members. The lateral torsional stability is there. The equation of Vlassov, or the terms of Vlassov are there. So that additional rotation, when it comes to that equation, so this means that we definitely need more safety in that area.
all right. So I have another question that just prepped up, maybe
Yes,
not in the context, but if you're talking about those historical buildings that are still so massively, greatly standing, right? So did
yes.
they have a similar kind of a workaround like Vaslo, or did they use Vaslo? Any idea? Because how are they still
Um,
built so strong against all the wind and storm?
yeah, that's very famous question everybody asks. That, oh, it's still standing. So this means that my work is correct.
Mm-hmm.
Now I wanna come to another part. What is the job of an engineer, of a structural engineer? The job of a structural engineer is two factors: safety and economy. It's not only safety, it's not only economy,
Yeah,
both together.
important
So
elements.
exactly. So we cannot go to economy if we are not ensuring the safety.
Mm-hmm.
I want to give you a more famous example: the Eiffel Tower.
Mm-hmm.
The Eiffel Tower in France. It's still standing for like more 100 years, more than 150 years probably. So that tower, if we're gonna check the design safety of that tower, is much more safer than it should be.
Mm-hmm.
If we are going to design it today, uh, probably we will end up by like 25 to 30 to 40% less steel than it is now.
Mm-hmm.
But it's
Mm-hmm.
still standing. But how much it is compared to our engineering today?
Got it.
Now, so if we're going to compare why this building is standing, because the engineering from 100 years in steel business until now, it's approaching to the safety and the accuracy slowly by experience.
Mm-hmm.
And this is why we are not really making that jump, the step, without really being sure that this step is safe first.
Mm-hmm.
Before being economic, it is safe. It is tested. It is passing. It is like this. It is like that. You see? And most of the equations of the code, before saying that this is theoretically correct, we are making the code's value is that experiments has been done, tests has been done. And this is where we are capable to put that equation in the code here and there, in the books here and there. So the safety comes first, then the how should I say the economy come second in a way. This is why
Mm-hmm.
all these buildings are standing, because
True.
the safety comes on the first rank, then the economy.
Prioritized element followed by
Exactly,
economy. If you
Yeah,
prioritize economy, you are pretty much just tarnishing or ignoring the most important part, which is the security part, right? Being safe.
exactly, exactly. But
Awesome.
research shall never continue.
Yeah.
Finding our missing point and our errors or our this should be like that. Another point in the code has always a safety factor, which is around zero point 0.6. So we have 40% the safety factor. So if our error now is about 2, 3% or 4%, so we have 40% the safety factor.
Mm-hmm.
We have loads, we are assuming loads on on those buildings higher than what it should be,
Mm-hmm.
because also there's another safety factor on those buildings. And this is one of the things, and on the material we have a safety factor also as well. So
Yeah.
all these factors comes together to keep our building safe. So if but this does not mean that we are not supposed to continue our knowledge and deeper and
Mm-hmm.
build our codes in a better way.
Awesome. Okay, one
Finally,
last
I'm
question.
living in that room, right? So
Yeah.
I'm sleeping in that room. I'm not thinking if that
Of
roof
course.
is going to fall on me, right?
Oh my God, don't put that in our heads. Right. So, one last question.
Yes,
What
please.
role does warping play in the torsional behavior of thin walled members?
Everything,
Mm-hmm.
everything. It's everything. A thin walled member like an eye section, edge section. Once it's
Okay, so
once we
what
have a torsion.
exactly is warping? Maybe you tell us what exactly is warping and then you go about this.
So if I have an eye section like that, I have
Okay?
upper flange, I have an eye and an eye. So
Mm-hmm.
that member, once it's subject to a torsion, it's
Mm-hmm.
rotating.
Mm-hmm.
So the upper flange and lower flange start moving in a different directions,
Direction. Mm-hmm.
like that. So
Mm-hmm.
that movement is a warping. So once they start moving, so they have a warping. Beside that warping, they are going to slide. This one is going to slide. That
Mm-hmm.
sliding is what I'm talking about.
Okay. So
That
pretty
has
much
not been
it's
considered by Vlassov.
everything like you said. Awesome.
Correct.
Okay. So any last
Yeah,
examples or
I
any
hope,
last thoughts on this?
yes, I hope that this research will reach as number as much as possible. And I would like to really continue that work personally or with the other teams and cooperate with other scientific people also as well to build to come up with a better level
Mm-hmm.
and to reach a higher level for in knowledge and technology and computer and also as well to build that information to share it with the whole world.
Right.
Finally, sharing the information is a value by itself.
Of course, of course. So you learn, you keep learning, there's no stop
Yeah,
to learning, and then you keep sharing, right? So the more you learn,
exactly,
the more you share. And that's how it
exactly,
is, the circle of life. Right. So,
exactly,
from
exactly.
my understanding, you did speak about your research, right? So, your research is delving more deeper into this concept in order to ensure how we can probably come up with a better solution to everything.
Correct,
Okay.
correct. And I have made an application for that on
Right.
the first floating island.
Mm-hmm.
I have made an application and it was fine. It was great. It has been built and
And even
it was
AI
very
was
great.
like, kudos to you, right?
Actually,
Right. It was
good.
amazing talking to you.
Thank
Thank you
you.
so
Thank you
much.
very
Thank you,
much.
Dr. Simon,
Thank
for
you, Ms.
sharing
Nada.
your
Thank you very much.
insights. Yes.
Thank
And
you.
this has
Appreciate it.
definitely been fascinating to kind of look into the transitional behavior and structural modeling. I'm sure
Sure.
our
Thank you.
audience has definitely gained a lot from your expertise. And
Thank
thank you
you.
so much. All the very best. And
Thank
yeah,
you.
keep giving yourself a pat on your back, not
Yeah,
just letting
thank you.
AI do that,
And I am
right?
really open for any conversation with whomever. If you have anyone who wants to know more, I'm really open. So I'm here. right? You know where to find me. Thank you
Thank
very
you.
much.
Thank you. It was amazing.
Appreciate it. Great. Thank you.
Amazing to have your insights. Thank you.
Thank you. Thank you. Bye bye.